Yeah, thank you for inviting me, and thank you all for coming to this session. It's been a long day, so I hope you have energy and some sugar to survive 2 more hours. So I'll talk about consensus, and I'll also publicize our group blog, Decentralized Thoughts. So if you get bored of me, Google Decentralized Thoughts and read the blog. It has some of the material that I'll talk about and some other material as well. So I'm going to talk about the consensus via the information theoretic lens. And why consensus? Well, this is a kind of a fundamental problem of coordination when you have failures. So whenever you want to make a decision between several parties and they want to get some joint decision and there are failures, then consensus is kind of the key tool to solve these problems. And this is kind of prevalent in multi-party computation as a building block. We're seeing it also in industry and in many core IT infrastructures. And obviously, you've seen the cryptocurrency and blockchain disruption also use this type of technology. And what we'll see in these 2 hours is kind of deep connections between ideas and approaches in cryptography and in distributed computing, and how cryptography and distributed computing, through this problem of consensus, interact with each other. So in particular, we'll see lower bounds for consensus, and lower bounds for consensus imply lower bounds for multi-party computation, because consensus is a type of a very simple function. As you know, when you build multi-party computation, you sometimes need a broadcast channel. So you use consensus as a building block for MPC. And it also goes the other way around. If you want to build efficient consensus protocols that sometimes use randomizations, then you use ideas and techniques from multi-party computation in order to obtain efficient randomized consensus protocols. All right, so with just a few words about myself. I do research in algorithms and distributed computing. And a good friend, cryptographer, called me a wannabe cryptographer. So this is not my background. Here this is an audience of cryptographers, so please be gentle with me if I make mistakes and not up to date with all the recent research in cryptography. All right, so any talk about consensus can't start without some hype around blockchain. So I'll give you my favorite quote. This is the person who controlled the Satoshi Nakamoto email about a month or two after the white paper came out, and is trying to explain something in an email, and says, the proof of work chain is a solution to the Byzantine general's problem. I'll try to rephrase it in that context. So it's nice to see that at least the person who was controlling the email understood that the core thing that's happening in Bitcoin, in the proof of work chain at least, is kind of solving the Byzantine agreement problem. Here's how I got used to this. This is Mark Andreessen. It's a venture capitalist. Writing in the New York Times, Bitcoin is the first practical solution to a long-standing problem in computer science called Byzantine general's problem. So as you can see, we have VCs talking about ideas in distributed computing on the New York Times. So these are interesting times that we are in. Okay, so what we're going to do today and tomorrow in terms of consensus. So the traditional way to kind of learn these protocols is kind of learning through islands. You learn kind of one protocol and the other protocol and then a third. And typically these protocols don't look very similar. They have a different look and feel. And what I'm going to try to do today is I'm going to try to give you a more unified view of several of these results today and tomorrow. So it's not going to be an historical survey. I'm going to kind of show you new ways to look at some of the older results. And I'm going to try to somehow highlight the connections between these different protocols. The idea here is that we want to understand these connections because this will give us a better understanding of the space. And one question you can ask, well, okay, if we're doing consensus, why not also look at non-information theoretic lens and look also at cryptographic primitives? And here, I want to agree with Benny and this whole goal of this Winter School, and quote this famous quote attributed also to Einstein, which is that you really want to see what is the simplest model where you can obtain results, and then you can try to lift up your ideas using stronger cryptographic tools. So understanding what is the basic things you can do just in the information theoretic setting gives you a lot of power of understanding and simplicity, which gives you more clarity. All right, finally, I'm going to talk about distributed computing and things related to consensus. And I'm going to give you more intuition and less rigor because there's a lot of details that I will not be able to give you in a single talk. I believe that you can learn by asking questions, so please ask me questions. Okay, I would be offended if I would just speak and nobody asks questions. So just in order not to offend me, ask me some questions during the talk. Okay, please. And finally, I believe that the only way to really learn things is by doing. So there's no shortcuts. You can't just listen. You have to kind of try to solve these problems yourself. So I will try to give you, some time where you can try to solve these problems by yourself. Okay, so here's the plan for today and tomorrow. So first, I'm going to use this opportunity to just tell you that I think we should all do multidisciplinary research. So it doesn't have to be, it's not just this workshop, but in general, multidisciplinary research. And then I'm going to do kind of a simple distributed computing 101, tell you about kind of the models of what is the adversary and what are the network models that are used. Define this problem of consensus. You probably know what consensus is, but I'm going to just define it very, very formally. And then talk about some protocols, some upper bounds. In particular, I'm going to start with this very famous protocol, which is named after a Greek island called Paxos. And this is going to be the starting point for a basic primary backup type consensus protocol. And then we're going to show how, using these gradecast approach, you can kind of lift this into a Byzantine protocol. So this is maybe, again, related to PBFT and hot stuff and protocols like that. And then what we're going to see is that you can take that type of protocol and add more techniques, in particular, this idea of some version of verifiable secret sharing, which gives you some sort of oblivious leader election and some sort of multi-world idea in order to lift this into a protocol that gives you a constant expected number of rounds, right? So these previous protocols, I have a clicker. These previous protocols give you a linear number of rounds, and this is kind of using randomization gives you a constant expected number of rounds. The same protocol we're going to use and then show that it can work also in partial synchrony. This is kind of the famous Paxos protocol that we're going to go over. And then, again, using kind of a variant of gradecast, which is called reliable broadcast, we're going to be able to do the same thing and get a Byzantine fault-tolerant solution in the partial synchrony model. This is really the PBFT and hot stuff type protocols. Again, everything here is going to be in the information theoretic setting, and we're going to eventually lift that into an asynchronous protocol that has a constant expected number of rounds. So that's the plan for 2 days. I'm not sure we'll get to this last part, but maybe in a high level. Okay, so I said, I'm going to give you a call for multidisciplinary research. So here's kind of my belief on, if you're interested in cryptography, you should also be interested in other things. So in particular, you should be interested in economics, which is kind of the study of scarce resources. You should obviously be interested in cryptography. Cryptography essentially is the study of protocols that replace trusted third parties. And the nice thing that we're going to do in the next 2 hours is talk about the relationship between cryptography and distributed computing. And here really the goal is to deal with how to tolerate failures, both in the network layer and in kind of large-scale systems. And finally, I urge you to look at it not only from an academic perspective, but also about how this technology is affecting the world. And so, study also the political science and law and public policy related to these technologies, because I think they are transforming the world, and it's kind of our responsibility to understand the effects of all these 4 things together. Okay, so enough advocation, and let's start with the distributed computing, and you can follow these 2 blog posts if you want more details. Basically, there are 3 basic models for distributed computing in terms of the network model. The most extreme model is this asynchronous model. In the asynchronous model, any message that's being sent, the adversary can delay any amount of time it wants. Okay, so if 2 honest parties send a message, the adversary can decide to delay it by 20 microseconds or 2 days or 2 months or 2 years. So it can delay the message any amount of time. That's kind of the asynchronous model. The next model, which is, I guess, more common, is the synchronous model. In the synchronous model, there is some known bound delta, and any message has to arrive in that time frame. So in particular, let's say delta is 3 seconds, then any message sent arrives in 3 seconds. The adversary can decide to send the message earlier than 3 seconds. So let's say, in a second and a half or in 2.5 seconds, and so on. But there's kind of a bound on the amount of time that it takes. There's even a simpler model than the synchronous model. This is the lockstep model. And this model simply, protocols run from one step to the other. Every message takes exactly one time unit, and computation essentially takes 0 time. And we typically write protocols in the lockstep model, and the world typically is what? Well, there's a debate, but it's definitely not lockstep, right? So maybe there is a bound on messages on the internet. So there's kind of a gap when you design algorithms. Think about what type of networking model you're designing. And indeed, one of the things that you need to look at is that this asynchronous model really captures worst case and is quite horrible, while the synchronous model gives you a lot more power. And so there's an interesting way to actually have a hybrid model in between them. And this is this famous partial synchrony model by DLS. This is Dwork, Lynch, Stockmeyer from '88. And the idea here is basically to say that the system has 2 phases. It starts asynchronously. So at the beginning, the system is completely asynchronous. Any message being sent takes an unbounded amount of time. The adversary can decide how much time it takes for this to arrive in an adaptive way. And then there is some unknown point in time. So there's an eventual point in time, which we don't know when. And this point in time is called GST. This is Global Stabilization Time. And at this point onwards, the system becomes synchronous. So what does it mean it becomes synchronous? There's a known bound delta, let's say 3 seconds, and every message being sent arrives at most 3 seconds. So this is kind of a halfway between asynchrony and synchrony, saying that the system starts in an asynchronous model and then at some unknown time becomes synchronous. Right? So are these 3 models clear? Yes? It looks arbitrary. So here's what I can say. A lot of people tried to write many different models. These 3 survive the test of time. So the first 2 are very natural. And in this bottom one, we'll talk a lot about it. It captures the requirement for protocols to be live in synchrony and safe always in asynchrony. So in a sense, that's kind of the core of what it captures. And it was suggested in '88, and it survived a lot of different other solutions. There's a different version which you can prove is equal for partial synchrony, which is that there's essentially some synchronous model, but you do not know, the person writing the protocol does not know what is the bound of synchrony. So essentially, the adversary can set this bound of synchrony before the execution, but after the protocol is defined. So if you think about the 4 different models here, you see that lockstep is kind of the easiest, and then synchrony, and then partial synchrony, and then asynchrony. So anytime you have a problem, in a distributed setting, you can try to solve it in all these 4 things and see when it becomes harder or easier, and so on. All right, so this is the networking model, and the next thing is there's an adversary, which is in addition to being able to delay some messages, this adversary can corrupt parties. And so again, this is kind of what is the power of an adversary? And so the simplest, weakest type of adversary is just a passive adversary, right? It runs the protocol, but maybe it tries to learn additional information while running the protocol. The next phase is a adversary that can actually crash some of the parties. So in particular, this adversary can decide to halt some of the parties midway while sending messages. So in particular, if they're sending a bunch of messages, it can decide that, let's say, the first 3 messages arrive, and then are being sent, and the 4th message and onward is not being sent because the system is crashing. The next type of failure model is this omission failure model. Also, think about it as kind of a bubble adversary. So essentially, the adversary doesn't control the node, but it kind of has a control of a firewall around this node. And so any message arriving to this node, or any message that this node wants to send outside, this bubble can decide whether it can drop it or allow it to pass. Okay, so this is the omission failure model. Obviously, omission is stronger than crash, because you can just decide at one point to stop all messages. But a omission adversary can also decide to selectively accept some messages or selectively drop other messages and so on. Sorry, was there a question? Yes. Yeah, so you can make a slight distinction between ingoing and outgoing omission, but typically, like the standard model says that you can control both. There's some small open questions around like this middle ones, but typically you can assume you can control both, which kind of makes sense. This is, for example, this is a good way to model secure hardware. Right, so if you have secure hardware, then you can't break into the, let's say, TPM that you have inside, but you can control the messages coming inside and out. More questions? Okay, good. So the next one is one that you obviously all know. This is kind of a malicious adversary that can control the party and do whatever it wants. I will just mention, two additional variants of this malicious party, which is a malicious party that's actually afraid of being detected. So these are this covert and epsilon covert, so afraid of being detected with some probability. These are interesting variants of detection notions. And again, you can see this hierarchy of different types of failures, where the easiest thing to do is run protocols against passive protocols and then crash. Omission, covert, and then finally Byzantine. So again, you can think about different protocols and you can try to solve them for different harder and harder types of adversaries. All right, so now I'm going to define this notion of consensus. This is a problem that was suggested back in 78. Leslie Lamport and his co-authors were basically trying to think about sensors in a mission to space, right? And what happens if some of the sensors get cosmic rays, and these cosmic rays cause some of these sensors to behave in a Byzantine manner. So the basic problem is that parties have some initial input, and they can send messages via point-to-point channels. Obviously, if they have a broadcast channel, then things become very simple for consensus. And here's the properties you want to obtain. So first property is this termination property, or liveness, where you want every party eventually to decide on some value. Okay, so this is kind of your first goal, just make a decision. And this decision is irrevocable. Once you decide, then you can't change your mind, right? Think about this as making some financial transaction, shooting some missile, making something that you can't recover from. And the second thing you want to do is you want to make sure, and this is where the consensus thing happens, this is the safety property, you want to make sure that no two non-malicious parties decide on different values, right? So we all decide on the same value. All right, so can somebody come up with a protocol that obtains these two properties? Yeah, exactly, decide on zero, right? So it's very easy to do these two properties if you just always decide on some default value. So these two properties alone are not enough. You have to have some sort of non-triviality that gives you two different choices of options at least two different choices of outcomes. And so this is this validity property. And so the validity property basically tries to capture the fact that the output of the decision has to be some function of the input. If it was not some function of the input, then we would kind of just have trivial solutions. So in particular, this is one type of weak validity property, which is that if everybody has the same value, so if everybody has 1, then 1 has to be the decision value. If everybody has 0, then 0 has to be the decision value. The problem with this type of validity is that, if we have conflicting values, then we can decide anything we want. So there are ways to make these validity properties stronger. Here is one which we will talk a little bit about later on, which is a fair validity, which basically says that we all have inputs. And in addition to kind of the simple validity property, we will say that with constant probability, some non-faulty, an input of a non-faulty party is the decision value. Okay, so this gives you somewhat stronger type of validity. Note that what is missing in these properties is a security guarantee, right? So we're not looking at what the adversary learns. We're not trying to hide this decision. So this is kind of the difference between these properties and what you would expect from a full multi-party computation protocol. So before I go on, it's important to kind of everybody understand what is the consensus problem, just to make sure that any questions? Good. Okay. yeah, so actually didn't want to show you the right side, but anyway, so this is one distinction is between broadcast and agreement. So basically, in both cases, we want to have safety and liveness, but in agreement, all we want is this validity property that says that if we all have the same input, then this must be the decision value. In broadcast, we assume there is a designated sender that needs to broadcast its message. And the validity property here is that if the sender is non-faulty, then its input is the decision value. Okay, so there's kind of a designated sender. And you know, what I wanted to ask is, what are the connections between broadcast and agreement? So can somebody tell me, if you have an agreement protocol, how do you implement broadcast? Yeah, so I think what you're answering is the following. If you have broadcast, right? If you have a broadcast mechanism and you want to implement an agreement protocol, then what you could do, you know, if you have a minority of failures, is you could have everybody broadcast their value and then say choose the majority value. Right? So this is kind of a way, if you have a broadcast, then you could implement agreement. So note that this reduction requires running a linear number of broadcasts. But I was asking a simpler thing. Let's say that you know how to solve agreement, but I want you to solve broadcast. So how would you solve broadcast? Yeah, so basically you would send, you know, the first round, the sender sends its value to everybody, and then the second round we run an agreement protocol. It's written here. So. It was supposed to be hidden, but it's testing you, right? If it's written here and you don't know it, it's okay. It's right. So here's the interesting question: if you want to get an upper bound, what would be stronger, an upper bound for broadcast or for agreement? And I guess you have to say why, because the answer is written. So why would you want to get upper bounds for agreement and not broadcast? I mean, in terms of complexity, if you have a solution for agreement, then broadcast adds a very little amount of additional cost to the reduction. Yes? Yeah, so every two parties have a point-to-point channel. Right, so basically, it's since this reduction from broadcast to agreement is frugal, you just use it once, then you want to get upper bounds for agreement and then lower bound for broadcast. This will give you kind of the strongest type of reductions when we'll talk about messages. Okay, so this slide summarizes essentially all of the results that we have for deterministic consensus, and at least the ones that I'll be speaking about here. So what you can see here is these two models, synchrony and partial synchrony. And here you have the different types of adversaries, so a crash adversary and omission adversary. And there's two types of Byzantine failures here, one which is, I will call it unbounded, and one other Byzantine adversary that for some reason cannot simulate honest parties, or cannot simulate too many honest parties. So in particular, if you had cryptographic tools, then potentially you couldn't simulate honest parties. But there might be other reasons. And so here's kind of the typical results. So if you just have crash failures, then you can actually deal with any number of failures in the synchronous model. However, if you have omission failures, then you can't deal with any number. There's a lower bound, which we're going to see, a very simple lower bound showing that you have to have a minority amount of failures. And we have these Paxos protocols that basically give you a tight upper bound in the omission failure model. In partial synchrony, what we'll see is that even for crash failures, you can't deal with more than with a minority. You have to have less than a minority of failures. So this kind of summarizes the crash and omission model. And now let's go and look at the Byzantine case. So in the Byzantine case, if you have an adversary that cannot simulate the honest parties, then you actually have protocols in the synchronous model that can work in the same bound as in the omission, which is that the number of failures can be less than a minority. Yeah, so we're going to see this lower bound, this FLM lower bound. This is this famous hexagon lower bound, where essentially in this lower bound, there are 6 parties. 2 of them are honest, and the other 4 have to be simulated by the adversary. So if the adversary can, in his mind, simulate 4 parties, then this lower bound holds, and then you can't do more than a third. But if you cannot simulate, then you can kind of get rid of this. In particular, yeah, if you have a PKI, you cannot simulate. If you have proof of work, you cannot simulate. This is why Nakamoto consensus works. But you can imagine other types of information theoretic settings where, for some reason, you cannot simulate the honest parties. There's a question here? Yeah, so yeah, this goes to this kind of hexagon lower bound, which we'll talk about, which basically says that even in synchrony, if the adversary can simulate honest parties, or let's say more honest parties than just itself, then you can only deal with 1/3 amount of failures. And you can get the matching lower bounds here. This is PBFT, and this is some synchronous version of this. And in partial synchrony, it doesn't even matter. So even if you have cryptographic assumptions, no matter what you do, you have this 1/3 lower bound for implementing consensus. Yeah, unless you have some sort of secure hardware, let's say a TPM and this type of stronger assumptions. So the interesting thing, I think, in these lower bounds is that, first of all, these lower bounds for consensus also give you lower bound for any MPC, at least in the point-to-point model. And these upper bounds, I think, are the same upper bounds that are obtainable also in the MPC setting in the malicious case. So it's kind of a case where consensus essentially gives you a full mapping of what's happening in terms of both consensus and more complicated functions. I will mention, so questions just about the threshold lower bounds? Yeah, so I'll mention 3 more important lower bounds. And so this is this FLP lower bound, which basically says that even if you deal with 1 crash failure, you will have to have infinite executions. So this means that if it's, you cannot solve consensus in the asynchronous model if you're not using randomization, because the deterministic protocol will essentially always fail. But if you used randomization, then you can deal with this by having this infinite execution have measure 0, right? So you can have constant expected number of rounds for solving asynchronous Byzantine agreement, but not with but not constant rounds. You have to have constant expected because there has to be some measure 0 probability of an infinite execution. All right, and this same type of a lower bound also applies for the synchronous model. So for synchronous model, you also must have executions that have at least t+1 rounds if you have t crash failures. So obviously, if you have t Byzantine, it's the same thing. So again, this means that if you're not using randomization, then you're bound to spend at least t+1 rounds in the worst case. And even if you are using randomization, you will have to have some measure of a long execution of t+1 rounds. Right? So there's no hope to do better than that. Yes?
How does the behavior change it if you don't assume that the number of participants is constant or a priori known? Like, so if you have a permissionless setting.
Yeah, so so if you
doesn't make sense the question.
Yeah, so I guess for me, if you decide to give every person that has a CPU 1 vote, then it's still there's still a population that's making votes. So, I mean, even if it's permissionless, you basically, yeah, it can change. Yeah, so I'm talking here about static lower bounds. And you can imagine these types of lower bounds will extend to cases where they change dynamically. Yeah, so I'm not going to focus on dynamically changing the membership here. More questions? Right, so this final lower bound that I want to mention is this, the fact that consensus requires a quadratic number of messages. And I think somebody asked yesterday, right, does VSS require a quadratic number of messages? So actually you look at consensus and you see that there are lower bounds that come from consensus that kind of force you to use a quadratic number of messages. And there are extensions of this type of lower bound for randomized protocols in kind of a weaker setting. So the next slide I'm going to move to is what can you do if you use randomization? So here we're going to introduce two new key features. One is using randomization, and the other is assuming that the channel, these point-to-point channels, are also private. So if I send you a message, then the adversary can't see the content of this message, right? So these are private channels. Obviously, you might need the cryptographic primitives to implement these channels, but this is kind of the assumption in this world, which is we're going to use randomization, and we're going to assume private channels. So as you can see, the results don't change that much in terms of the lower bounds. So all these lower bounds hold. For the upper bounds, what you can see is that you get this new type of results where the expected running time is constant. So the expected running time is constant here. This is kind of this results of Katz and Kuh. In the Byzantine case, this is Mikhaili and Feldman, and later again in Katz and Kuh, constant expected time for synchronous protocols. So again, even though the lower bound says that there has to be executions of t+1 rounds, you can reduce the measure of that to be small so that you have a constant expected number of rounds. I guess in partial synchrony, you can get the same type of results. And in asynchrony, you can use randomization to get the same type, essentially the same type of results. So in omission failures, you can essentially do the same thing. Again, the question here is how you measure time in an asynchronous model. So there's a way to essentially measure rounds or time in an asynchronous model that is meaningful, that essentially explains what is a constant round protocol here. Maybe the last twist is the optimal results for the Byzantine model in asynchrony, where here if you assume that the adversary controls less than a quarter, then you have constant expected solutions. Or if you assume that the adversary controls less than a third, then you have solutions that have a polynomial expected running time. And there's kind of a middle solution where there's actually a non-zero probability of deadlock. But condition on not having a deadlock, it's a constant expected running time. And I want to highlight this lower bound. This lower bound is Ben-Or, Kelmer, and Rabin from '94, which basically says that if you have a verifiable secret sharing scheme that can handle less than an adversary that controls more than a quarter, then it must have an error. And not only it must have an error, it must have a non-zero probability of getting stuck, of being non-terminating. So this is a case where the consensus lower bounds don't match the MPC lower bounds. If you want to implement MPC, you actually have to implement both consensus, which you can do with no error. But you also have to implement verifiable secret sharing. And this requires an additional cost of not just having a measure 0 of non-termination, but actually having a positive probability of non-termination. Okay, questions about the randomized results? Yes? Yeah, so to get constant expected time, you want to hide from the adversary some of these messages. In particular, we're going to see you have to randomly elect a leader. So those messages you have to hide from the adversary. If the adversary is omission, failure, and adaptive, then it will force these protocols to run for f+1 rounds. So in a sense, you have to hide at least some messages, even from the omission model, in order to get the constant expected number of rounds. Yes? No, I'm not aware. What are you referring to? I see. So I apologize. I'm not aware of that. I will say, there is a model where the adversary you have no private channels, right? So this is kind of the model where the adversary can see all messages. It's a different model, which I'm not going to talk about today. Even harder to get results there. More questions on this slide? Good. Okay, so I promised you to wake you up a little bit. So what I'd like you to do is think about a protocol that has 3 parties. The adversary can choose which party adaptively to corrupt. And the corruption is an omission failure model. And you have a notebook, so you can try to write down a protocol that solves consensus. And I'm just reminding you what is the properties of consensus. So first of all, I want to obtain safety. And here I want you to get uniform safety, which basically means that even if a party is omission failured, if it reaches a decision, it has to reach the same decision as everybody. And secondly, I want you to have this protocol which reaches decisions for all the non-faulty parties. And validity, right? So if you all start with some value, then you all should decide on that value. And again, in a lockstep model, so in the synchronous model, the simplest one that you can, you have pens and papers. Try it out. Think about it. You can even talk to your friends in the table if you want to have a joint solution, or you can have your private solution and compete against your table members. So try to solve consensus. Yeah, so people ask, what is omission failure? So omission failure is when the adversary has a bubble around the party, and every message arriving or every message leaving this party, the adversary can decide whether to drop it or not drop it. Okay? And since I don't need randomization, let's say that the adversary can see the content of this message. Okay, so there's a bubble around the party, and the adversary can decide to either drop it or not drop it. Every message. Separately. Adaptively means it can decide the action based on everything that it saw in the history. Okay, so I'm gonna force you to stop. I know it's not a lot of time. I guess I was a bit slow on the first part. So I'll let you think about it offline. This is a room full of cryptographers, so you might come up with new, better solutions that were than 30 years of research. So I'm a bit worried, but you should be able to spend, let's say, you spend 5 minutes. So let's say if you spend 10 minutes, you should at least realize that there are some ways to make mistakes. And maybe you will have some good approaches just by a raise of hands. So how many have a solution that can solve this in 1 round? 1 round. No. Okay. In 2 rounds. 2-round solutions. 2 rounds. 2 rounds. Okay. This is a smart audience. Maybe not. Maybe not. Okay. 3 or more rounds. Any table that feels they have a solution. They have a solution. No. Okay, so I'll let you think about it. It kind of shows, it's actually a very simple problem. Maybe I should have just asked you for crash failures, not omission. Even simpler. So you can't do it in one round, right? There's a lower bound of t plus 1 rounds, right? So for crash. So that kind of helps you. Hopefully we'll even see this lower bound. And yeah, you can actually do it in 2 rounds, and we'll show a version of that in 2 rounds, even in the Byzantine case, right? This is kind of a nice, simple protocol. But for now, I'm going to take an approach which is very different than the approach that you tried. So what I would ask you to do is, this is a good homework. Try to think about it, and your task for tomorrow morning is to come up with a protocol that solves this problem in 2 rounds. 2 rounds, okay? That's the homework. If you can do it in more, that's also good, but don't do it in 1 round. Okay, so what I want to do now is actually give you a very different type of solution approach, in a sense that, maybe some of you actually, this is the approach you tried, but, it's conceptually strange initially, because you probably tried some sort of symmetric problem where everybody sends to everybody, and everybody just chooses some majorities and so on. But what we're going to try to take is this primary backup approach. And the reason we're going to take this primary backup approach is that it has a lot of advantages. First of all, it's used a lot in practice. Second of all, it's efficient in the randomized case. So the primary backup approach is kind of a very nice way to break symmetry by choosing one person to make decisions for all the other replicas. Right? So we all do this a lot. We kind of nominate one person, and this one person makes a decision, then we all say, okay. So this is kind of this primary backup approach. And we're going to study it first in the omission model and then in the Byzantine model. And the primary backup approach works in views. So the system has views, and in each view, there is one party that's designated as a primary. So think about it just like general elections. Right? So every, let's say, 3 months, we choose a new primary, and then again, after 3 months, we choose a new primary, and so on. This is kind of and then we move from one view to the other view. You can do it 4 years also, but here we like less. Okay, so one is primary, and the other is backup. And for simplicity here, we'll just round robin. We'll take all the people elected, and we'll just round robin them one by one in a rotating coordinator. And there's many other options, a randomized leader election, so on, that we'll do later on. Other versions. Okay, so first what I want to say is why this is impossible to solve, why I didn't ask you to handle 2 parties, and I asked you to have 3 parties. So why are 2 parties impossible? So this is kind of this very simple split brain lower bound of Dwork-Lynch-Stockmeier, which basically says that here is one world where the messages between A and B are just delayed. Remember, in the partial synchrony model, initially messages can be delayed by an arbitrary amount. So in the middle world, there are no messages between A and B. In the left world, A is omission failure and B is correct. And so, there's still no messages, but A is the one that's failed. In the right world, it's the opposite, right? So B is failed and omission failure. And the omission failure blocks all messages. And A is correct. And so in all 3 of these protocols, nothing happens and there's no communication. But if we assume there is a protocol that solves this system, then obviously it will solve it in this world. And let's say it'll have to use at least the value that B has for validity. So if B has 0, then in this world it'll have to decide 0. And in this world it'll have to decide 1. Let's say if A has 1. And then if you look at this middle world, there's no way to distinguish between this middle world and this left world for A, and this middle world for B, and this right world for B. So basically, this is kind of a simple way to show 3 worlds where in one world B has to decide, let's say, 0. In this world, A has to decide 1. And in this joint world, what will happen is that both of them will have to decide conflicting values. And so we've broken safety. And so this is kind of a very simple lower bound that is using the fact that the system can be asynchronous. And because of that, we have this middle world that can delay messages in an arbitrary amount. We can do the same thing in synchrony, and this is why I asked you to solve uniform consensus. And in uniform consensus, what I said is that if both A and B decide, in particular if B decides, it doesn't have to decide, right? Because we only want the non-failed parties to decide. But if B does decide, then we want it to also decide the same value as everybody else. This is the uniform consensus property. And for uniform consensus, you can do the same lower bound by just looking at these two worlds, right? So in these two worlds, again, there's no communication, and they have to decide, both of them, both A and B, and they will both fail. So this is, again, a lower bound showing you why you have to have less than a minority amount of failures in the omission model. All right, so unlike the previous day, the day before this talk, which used very complicated mathematics, here we're going to do very, very simple things. So I apologize in advance. Things are very, very simple here. We're just going to use this pigeonhole principle, right? So this is a quorum intersection property. And really, there's only one riddle you need to solve. And you have a set that has n elements, and you take two subsets of size n minus f. F is some parameter. So you take two subsets of size n minus f, and the question is how many elements are there in the intersection? How many? How many? N minus 2f, yes. So this is the only math you need, okay? So why do you need, why is this the case? So you can maybe draw it and see that if you have n minus f, then for one set, then the other set, well, it can put f outside of this set, but then it has at least n minus 2f remaining elements that have to go to the first set. So the intersection is n minus 2f. Again, this is kind of pigeonhole principle. This is the only math that you will need for these protocols. So again, I apologize in advance. It's very, very simple. So let's look at two particular values. So if you have n equals 2f plus 1, and we take two sets of f plus 1, then they must intersect at one element, right? This is kind of just the same thing. And the second specific case we'll look here is if we have a group of 3 f plus 1 parties, and we choose quorums of size 2f plus 1, then the intersection is at least f plus 1, right? So we're going to use this in the Byzantine setting. So in the omission setting, we're going to use the first, and the Byzantine, this second property. Okay, that's the only thing we're going to use. So let's try to build a protocol. So let's do the same thing that you guys did, but we'll do it together. So here's my initial protocol. So there's a primary. Let's say I'm the primary, and what I do is I receive my input, and I decide my value. That's always valid because you're allowed to decide your value. That won't break validity. And after you decide your value, you send a message telling everybody that you've decided. Is that good? Why not? Yeah, so the problem is that as an omission failure, I can't first decide and then send a message because maybe these messages won't get through. Yeah, so the next idea is to say, well, I'll first send a message, and only then I'll decide. How about that? Does that work? Yeah, there's no difference, right? So from a omission failure property, there's no difference between first sending and then deciding. So really what is missing here is getting an acknowledgement, right? And this is the final key that we'll use, is we'll send messages, receive acknowledgements, and then do something. And the core challenge that we need to deal with is exactly this problem of what happens if the primary decides on a value, and then because it's failed, a new primary has to make sure that it's deciding the same value that the old primary decided upon. So this is kind of our goal. Benny, how much time do I have for a break? It's about time. Okay, so what we're going to do after the break is talk about this view change protocol. And this view change protocol is kind of the core of these protocols. It allows you to safely move from one primary to the next primary. The idea here is that as a primary, I don't always have to use my value. I sometimes look at the network, ask queries, and decide to use a value that I've heard from somebody else. Because maybe the previous primary has decided on some value, and now I have to adopt this value. And so there's 3 challenges, and we're going to solve them after the break. The first is that you want to make sure that if you make a decision, then this decision will remain even if you are faulty. So somebody else can read this decision. And then you want to make sure that this view change protocol has these safety and liveness properties. So in particular, if you do a view change, you don't get stuck just waiting for responses. And it's safe. It means that if I receive the value, I know it's a safe value that I can actually use. So after break, we're going to kind of deal with these 3.